Hello friends, I am Dr. Ankur Vaid, Assistant Professor from Pharmacy College, UP RIMS and R, Safai, Etawah, UP. Today we are going to deal with an interesting and learning episodes of B.Pharm on the important title Phase 2 Cholinomimetics. So let's start our episode while taking a look at what we are going to learn today. We will begin with the general introduction of the topic, followed by acetylcholine biosynthesis, its storage, release and metabolism. After discussing it, our lecture will proceed further to anticholinesterase, classification of parasympathomimetics and their pharmacological action. So let's start our today's lecture with introduction of this topic. Introduction. Parasympathetic nervous system. The autonomic nervous systems or ANS is the portion of the nervous system that contains involuntary process. The ANS regulate the vital functions of the body including blood pressure, body temperature, water balance, urination, digestion and many others. The parasympathetic, usually abbreviated as PSNS, and sympathetic nervous system are the two divisions of the autonomic nervous system. Parasympathetic nervous system arises from the central nervous system. Parasympathetic outflow comprises both cranial and sacral components. The cranial components includes oculomotor nerve, facial nerve, glossopharyngeal nerve and vagus nerve, while the sacral outflow is carried in spinal nerves in the sacrum S2 to S4, also act as parasympathetic nerves. The parasympathetic system is responsible for the stimulation of rest and digest or feed and breathe activities that occur when the body is at rest, especially after eating, including sexual arousal, salivation, urination, digestion and defecation. Its action is described as being complementary to that of the sympathetic nervous system, which is responsible for stimulating activities associated with the fight or flight responses. Neurotransmission. Nerve impulses elect responses by liberating a specific chemical called neurotransmitter. These neurotransmitters allow the transmission of signals from one neuron to the next across synapses. Neurotransmitters are essential chemicals inside the body that direct your heart to beat, your lungs to breathe, and your stomach to digest, etc. They can also affect mood, sleep, concentration, weight, and can cause adverse symptoms when they are out of balance. Two types of neurotransmitters are inhibitory and excitatory. Inhibitory neurotransmitters calm the brain and balance mood, while excitatory neurotransmitters stimulate the brain. There are many types of neurotransmissions and they are named for their specific neurotransmitter involved. Parasympathetic nervous system involve cholinergic transmission, that is the release of acetylcholine and its activation of the postsynaptic receptors. Things that bind to and activate receptors are called agonists. Thus, acetylcholine is the endogenous agonist for all cholinergic receptors. Acetylcholine is a major neurohormonal transmitter at the autonomic, somatic as well as central sites. The cholinergic drugs are chemicals that act at the same site as the neurotransmitter in acetylcholine and stimulate parasympathetic nervous system. Thus, these drugs are also called parasympathomimetics or cholinomimetics. Acetylcholine is an ester of acetic acid and choline. Acetylcholine is a neurotransmitter in autonomic nervous system, serve as an internal transmitter for the sympathetic nervous system and as the final product released by the parasympathetic nervous system. The overtransmission of acetylcholine can have very dangerous effects ranging from paralysis to convulsions. In spite of peripheral, the brain contains a number of cholinergic areas EAH with distinct function, including arousal, attention and motivation. A number of chemicals, venoms and toxins alter the effect of acetylcholine. Module 1. Acetylcholine synthesis. Acetylcholine is the acetic acid ester of choline. It is synthesized locally in the cholinergic nerve ending from acetyl coenzyme A, that is acetyl-CoA, which is synthesized from glucose and choline. The reaction is catalyzed by choline acetyl transferase. Choline is present in plasma at a concentration of about 10 millimolar and is actively taken up by the axonal membrane by sodium choline cotransporter. Acetylcholine synthesis takes place in 3 steps. Step first is proceed in mitochondria. Acetate combined with ATP to form adenyl acetate. In step second, it is proceed in axonal cytoplasm. Adenyl acetate combines with coenzyme A to form acetyl coenzyme A. Step third, acetyl coenzyme A combined with choline in the presence of choline acetylase produce acetylcholine and release coenzyme A. About 10,000 molecules of acetylcholine are packaged into EACH vesicles which are about 300 to 600 angstrom units in a diameter by a vascular acetylcholine transporter. If the cell does not have enough choline, acetylcholine synthesis does not proceed. Coenzyme A is widely distributed in body and choline is an essential dietary constituent belonging to B complex group of vitamins. Hemicholinum blocks choline uptake, that is the rate limiting step in acetylcholine synthesis, and depletes acetylcholine. Most of the acetylcholine is stored in ionic solution within small synaptic vesicles, but some free acetylcholine is also present in the cytoplasm of cholinergic terminals. Active transport of acetylcholine into synaptic vesicles is affected by another carrier which is blocked by vasamicol. Now, acetylcholine storage. Acetylcholine is produced throughout the neurons which is stored in the synaptic vesicles which are mainly accumulated at the nerve ending. One way of decreasing the amount of acetylcholine in the cell is to block the choline transporter. The vesicles contain both acetylcholine and ATP with a ratio of about 10:1 in the float phase with calcium and magnesium. In some cholinergic vesicles, peptides are also present that act as co-transmitter. The vesicular acetylcholine transporter is saturable and is ATP dependent. The process is inhibited by vasamicol and is non-comparative and reversible. Estimates of acetylcholine content of synaptic vesicle range from 1000 to over 50,000 molecules per vesicle. A single motor nerve terminal contains 3 lakh or more vesicles. Now, acetylcholine release. Acetylcholine is released into the synaptic cleft. Release of acetylcholine and co-transmitters, that is ATP or VIP, occurs following depolarization of the membrane, which allows the entry of calcium through voltage dependent calcium channels. Elevation of inward calcium plus ion promotes fusion of the vesicular membrane with the cell membrane and exocytosis of vascular content. This fusion process involves the interaction of specialized proteins of the vascular membrane, that is VAMPs, termed as vesicle associated membrane proteins, and the membrane of varicocytes, that is SNAPs, synaptosome associated proteins. A selective inhibitor of acetylcholine transport, Vasamicol, inhibits vascular acetylcholine uptake. Vasamicol blocks the evoked release of newly synthesized acetylcholine without significantly affecting high affinity choline uptake. Acetylcholine synthesis or calcium ion influx. The fact that acetylcholine release is lost secondary to the blockage of uptake by the vesicle strongly suggests that the vesicle is the site of acetylcholine release. The exocytotic release of acetylcholine can be blocked by botulinum toxins. Once release of acetylcholine can interact with the muscarinic receptor, which are GPCRs of nicotinic receptors, which are ligand-gated ion channels, to produce the characteristic response of the effector. Module 2. Acetylcholine hydrolysis. There are two types of cholinesterase, acetylcholinesterase and butyrylcholinesterase. These cholinesterase differ in their location in the body and their substrate specific. Acetylcholinesterase is strategically located at all cholinergic sites and serve to inactivate acetylcholine instantaneously, while butyrylcholinesterase present in plasma and elsewhere probably serve to metabolize ingested esters. The released acetylcholine is hydrolyzed by the enzyme acetylcholinesterase, produced inactive metabolites choline and acetate. This enzyme acetylcholinesterase is abundant in the synaptic cleft, and its role in rapidly clearing free acetylcholine from the synapse is essential for proper muscle function. The metabolite choline is recycled by sodium choline transporter. Acetylcholinesterase is concentrated in the synaptic cleft, possess high catalytic activity, usually about 5000 molecules of acetylcholine per acetylcholinesterase molecules per second. The hydrolysis of acetylcholine by acetylcholinesterase initiates by the formation of reversible enzyme substrate complex. In the first stage, the cationic head of acetylcholine is adsorbed on the anionic site of acetylcholinesterase molecule and form a salt. The ester group of acetylcholine is adsorbed on the esteric site of the acetylcholinesterase molecule. Acetylcholine is thus adsorbed on the enzyme to form a substrate enzyme complex. The second state of the hydrolysis involves splitting. The substrate enzyme complex reacts to release choline and leaves an acetylated enzyme. The third stage of hydrolysis leads to regeneration of the enzyme. The acetylated enzyme reacts with water to give acetic acid and liberates the enzyme. Thus, the enzyme is regenerated. The acetylation rate is the slowest step in this sequence and is the rate limiting. Acetylcholinesterase. Cholinesterase are the member of family of enzymes responsible for the hydrolysis of acetylcholine. Various types of esterase are found in body, but only two are discussed here. The first, cholinesterase, is true or specific cholinesterase or acetylcholinesterase is the enzyme that hydrolyzes acetylcholine liberated at the nerve ending. It is found in the nervous tissue, human placenta and erythrocytes. The second cholinesterase is pseudo-cholinesterase or non-specific cholinesterase, found in the blood, serum, intestine, skin and many other tissue. Usually, it is believed that pseudo-cholinesterase not participate in hydrolysis of acetylcholine. As we have previously discussed that acetylcholine esterase is the hydrolytic enzyme of acetylcholine. This acetylcholine esterase play a vital role in normalized conduction by hydrolyzed acetylcholine at synaptic cleft. Inhibition of acetylcholine esterase prolong the duration of neurotransmitter in the junction and produce pharmacological action similar to those observed when acetylcholine is administered. These inhibitors are indirect acting cholinergic agonists. Acetylcholine esterase inhibitors are used in the treatment of myasthenia gravis, atony in the gastrointestinal tract and glaucoma. Two types of acetylcholine esterase have been discovered and reported. These include reversible and irreversible anticholine esterase. Example of reversible anticholine esterase include physostigmine, neostigmine, pseudostigmine, ambinonium, idrophonium and distigmine, while irreversible anticholine esterase include organophosphorus compounds like diisopropyl fluorophosphate, icothiopate, tetraethyl pyrophosphate, malathion and parathion. Certain natural neurotoxin work by inhibiting acetylcholine esterase, thus leading to excess acetylcholine at the neuromuscular junction, causing paralysis of the muscles needed for breathing and stopping the beating of the heart. Module 3. Cholinergic receptors. Friends, before moving to our next module, that is about cholinergic receptors, I would like to suggest you to visit our website www.cec.nic.in for further reading and learning of more topics associated with your B.Pharm syllabus. Here you will find many lectures, e-content, FAQs, LORs and many more. Hope this site will be a catalyst of learning for you. Now friends, let us discuss cholinergic receptors. Cholinergic receptors can be classified into two categories. Category first, muscarinic receptors. These receptors are located into tissues innervated by postsynaptic parasympathetic nerve, sweat glands and blood vessels. Muscarinic receptors are G proteins coupled receptors having 7 proteins helix that transcend the plasma membrane, creating 4 extracellular domain and 4 intracellular domains. Acetylcholine binds with the extracellular domain while intracellular domains coupled with G protein to initiate biochemical changes which results in pharmacological action. Nowadays, 5 distinct types of muscarinic receptors have been isolated on the basis of molecular cloning, abbreviated as M1, M2, M3, M4 and M5. The binding of acetylcholine to muscarinic results the stimulation or inhibition of the organ system effect. This consequence the secretion from salivary and sweat glands secretion and contraction of the gut and construction of the airway of the respiratory tract. It also produces contraction of the heart and relax smooth muscles of blood vessels. Second, nicotinic receptors. These receptors are located in the autonomic ganglia, the neuromuscular junction, the adrenal medulla and in the CNS. Nicotinic receptors are categorized into two types, that is N1 or NM and N2 or NN. N1 or NM receptors are located at neuromuscular junction stimulated by phenyl trimethylammonium and blocked by succinylcholine and D-tuberculorin and decamethonium. N2 or NN receptors are found in autonomic ganglia stimulated by tetramethylammonium and blocked by hexamethonium and trimethophan. Now friends, let us discuss cholinergic drugs. Cholinergic drugs or cholinergic agonists or parasympathomimetics are class of compounds produce alike action of acetylcholine. They possess same pharmacologic action as neurotransmitter acetylcholine. Cholinomimetics are classified into two groups on the basis of their either direct action or indirect action. First category, direct acting cholinergic. These drugs are further classified into two subgroups. Group first, the drugs of this category stimulate structures innervated by the preganglionic synaptic fibers. Example includes acetylcholine, methacholine, carbamylcholine and bethanechol. Group second, cholinomimetics alkaloids. Cholinomimetic alkaloid stimulate structure innervated by the postganglionic parasympathetic fibers. Example of this category are pilocarpine, muscarine and ericoline. Second category is indirect acting cholinergic. The drug of this group inhibit cholinesterase and thus also called anticholinesterase. The members of this groups are further classified into two categories. Category first, reversible anticholinesterase. The action can be reversed by high concentration of cholinesterase, thus called reversible anticholinesterase. Example of these groups are physostigmine, neostigmine, pseudohistamine, amminonium, idrophonium and distigmine. Second category, irreversible anticholinesterase. The action of this group member cannot be reversed by cholinesterase and thus the member of this group is called irreversible anticholinesterase. Example of this group is diisopropyl fluorophosphate, icothiopate, tetramethyl pyrophosphate, malathion and parathion. Module 4, Pharmacological action. In Module 4, we will discuss pharmacological action of acetylcholine. Acetylcholine stimulates both muscarinic and nicotinic receptors, thus having wide spread of activity, therefore lack of clinical value. Acetylcholine is rapid hydrolyzed by acetylcholinesterase, which also make the compound a little or no therapeutic value in spite of acetylcholine. Therapeutic importance, it acts on both muscarinic and nicotinic receptors and produce pharmacological action. The muscarinic action of acetylcholine is predominant action on blood pressure, while nicotinic action is unmasked only on the atropinization of the animal. Now let us discuss muscarinic action. The muscarinic action of cholinomimetics are summarized here. First, on heart and blood vessels. Acetylcholine slowing the heart and arterial vasodilation in slight higher doses and a fall in blood pressure. Second, stimulation of the smooth muscles of the bronchi, the gastrointestinal tract, the gallbladder and bile duct, urinary bladder and uterus. Third, relaxation of sphincters in the gastrointestinal, biliary and urinary tract. Fourth, stimulation of the salivary, sweat, nasopharyngeal and lacrimal glands and stimulation of the secretory activities of the stomach, intestine and pancreas. Fifth, construction of the pupil or meiosis and accommodation of the lens for near vision. The muscarinic action of acetylcholine is blocked by atropine and other anticholinergic drugs. They are mimicked by methacholine, carbacholine and pilocarpine, muscarinic and ericoline. Now, nicotinic action. The nicotinic action of cholinomimetics are summarized here. First, stimulation of the skeletal muscle. Second, stimulation of the synaptic and parasympathetic ganglia and stimulation of the adrenal medulla. The nicotinic action of the acetylcholine is blocked by curare, that is D-tuberculonin at neuromuscular junction and by ganglion blocking agents. First drug, neostigmine bromide. Neostigmine is the naturally occurring anticholinesterase drug. It is hydroxyphenyl trimethyl ammonium bromide dimethyl carbamate. It is quaternary ammonium compound shown reversible anticholinesterase activity. Neostigmine is used as an antidote to non-depolarizing neuromuscular blocking drug and in the treatment of myasthenia gravis. It is irregular, absorbed from gastrointestinal tract, and it does not cross the blood-brain barrier. The irregular absorption of neostigmine may produce some problems but minimize CNS toxicity. Neostigmine shows action on both receptors including nicotinic and muscarinic, but its nicotinic action is predominant over muscarinic. Neostigmine Module 5. In Module 5, we will discuss various parasympathomimetic drugs. First, methacholine chloride. Methacholine is the acetyl ester of alpha-methylcholine. Methacholine differs from acetylcholine chiefly in its greater duration and selectivity of action. The more prolonged action of methacholine is due to the addition of methyl group, which increases its resistance to hydrolysis by cholinesterase. Methacholine is a selective N2 receptors agonist and devoid of any nicotinic effect. Although methacholine can exist in nature as both R and S isomer form, however, the pharmacologic activity resides in S isomer. The ratio of potency of S/R isomer was found to be 240:1. Methacholine chloride may be prepared by the addition of propylene chlorohydrin to trimethylamine, which on acetylation with acetic anhydride yields the official compound. Methacholine chloride may be administered orally, but it is poorly and irregularly absorbed. The unpredictability of absorption and intensity of response has prohibited its use as a vasodilator or cardiac vagomimetic agent. Methacholine can be used for diagnosis of bronchial and occasionally used to terminate paroxysmal supraventricular tachycardia, but is obsolete now. Methacholine chloride occurs as a colorless or white crystalline powder. It is odorless or has a slight odor with freely soluble in water, alcohol or in chloroform. It is hydrolyzed rapidly in alkaline solutions. The solutions are relatively stable to heat and will keep for at least 2 or 3 weeks. Summary. The autonomic nervous system composed of two divisions, sympathetic and parasympathetic nervous system. Acetylcholine is the neurotransmitter of parasympathetic nervous system produced by choline with acetyl coenzyme A. This acetylcholine is synthesized in synaptic vesicles and released at neuronal junction, where it binds with receptors and produce their effects. Usually muscarinic and nicotinic are two types of adrenoceptors. Acetylcholinesterase hydrolyze acetylcholine at nerve junction and abolish its action. A number of parasympathomimetic drugs have been discovered produce similar action as acetyl.